So here is the topics that we are going to cover in chapter 7. Right? So basically it's how to deal with a linear system of algebraic equation, right? How we can solve them basically. And so of course we will have to learn about matrices and vectors. That's the first step. So what is a matrix? Is basically a matrix is a table of those numbers. They are divided by rows and columns. Rows and columns. Rows come first. So when this is called basically 2 rows and 3 columns. Alright? And some of them are square matrix like 3 by 3 or 5 by 5. Some of them are not 2 by 3, right? Or this guy would be 1 by 3, and this guy would be, right? So always the row first and then the column. And those, each one of those guys are the entry or the element, right? So those entries or element could be number or could be symbols or cosine theta minus sine theta. Very good. So again we said it's basically the row first and then the column. So this guy is called 2 by 3. And those on the diagonal are pretty important. We know why in this course. This is called the main diagonal, alright? And again this is a square matrix. 2 by 1, 1 by 3, that's a square one, alright? So a square versus rectangular matrix. So this is square, this one is rectangular. Now where are those tables of numbers come from? Where do they come from? I think there it says why it come from. It should be where are they coming from. So where are they coming from? They come from those system of equations. Alright, so look at this. This is basically a 3 equation in how many unknown? 1, 2, 3. Well, some of equations don't have 3 variables, but still the system is 3 equations, 3 unknown. Alright? So you can write this as basically you take the x1, x2, and x3 and put them in a vector like this, and then the coefficient matrix would be basically this, A. And this vector here, that column vector, that's the B. So the B is like 6, 20, and 10. And what is this A? It's the number that's here, 4, 6, 9, 4, 6, 9, 6, nothing here in x2. x2 doesn't show up. So that's why it's 6, 0, and minus 2. Right? And then 5, minus 8, and 1. So this is a coefficient matrix. Right? So any one of those elements, we can also call it Aij. So for example, this guy would be A23 because that's the A in the second row, third column. And this guy would be A33. Of course, this guy would be, what's that guy? A22, right? A22, and that's A11. Very good. Now, so this is the coefficient matrix. If you stick the B next to it, like this, and you put a dotted line like this, or you don't put the dotted line, still if you just stick B next to A, then that's not A anymore, right? That's A with B next to it. This is called the augmented matrix. It's like a super big A. It's not the A, it's the A next to the B. It's convenient sometimes to have this rather than just the A, because if we have A and B next to it, then we can do operation on them all at once. Alright, so this is a whole system in one matrix, and then you can give it to MATLAB and tell him, here, solve this for me, for example. Very good. So we'll give it this symbol. Look at this wiggle thing. So this is a wiggle like this, and this is augmented matrix. Alright? So where else they can come from? They can come from, for example, look at this example. This is basically 3 activity: walking, biking, and jogging. And this is the number of hours per day that you spend. On Monday, 1 hour here, 0 hour here, 0.5 hour there. This is the number of hours you spend every day on those 3 activity. And this is how many calories per hour for 350 for biking, 500 for walking, and this guy 950 in say jogging. So then if I multiply this by this, if I multiply that row by that column, I get the 825. 1 times 350 plus 0.5 times 950, that's 825. So that would be how many calories I spend on Monday. That's how we multiply matrices. Actually, you multiply the rows by the column. to come up with this. So I'll spend more time on this later. But the point is, then this matrix multiplying it by another one will give you something that you want, right? Same thing here. Actually, when you think about it, if you multiply the A by the X, you should get the B, meaning x1 times 4 plus x2 times 6 plus x3 times 9, you should get the 6, right? That's the first equation basically, right? This is linear transformation. Basically, say if you have a vector x1 and x2, so you have an image and you would like to rotate that image on the screen, right? So here is one point in that image, this say that vertex of that star, for example, and you want to find out what is if you rotate theta degree, 10 degree, 20 degree, whatever, where will it end up going to? Where is this y2 and y1? Well, you can actually do try to find the geometry and say, well, to get y2 and y1, well, y2 would be this r cosine, sorry, y2 would be the r sine theta plus psi. y2 is r sine theta plus psi, right? It's the whole, psi is the original angle and theta how much did you turn. So r cosine this, the whole thing would be y2, and then if you remember sine theta plus psi, that's basically, or sine a plus b, that's sine cosine plus cosine sine. And then you tell yourself, well, what's sine psi and what's cosine psi? That's the original angle, and the sine would be r and x2, so the sine is x2 over r, and the cosine would be x1 over the r. So x1 over the r and x2 over r, and then you cancel this one and cancel that one, and you do the same thing for y1. Rather than all this, the matrix that will turn x1 to x2 is basically simply this. When again those two equations, if I just cancel this r with this r, now I have y2 and y1. y2 is x2 cosine theta plus x1 sine theta. y2 is x2 sine theta plus x1 sine theta plus x2 cosine theta, and y1 is x1 cosine theta minus x2 sine theta. y1 is x1 cosine theta minus x2 sine theta. All right. So this matrix basically can turn any point, any x1, x2 vector to its basically y1, y2 vector. All right. So that's why they are useful. We can use them for solving equation. We can solve them. Use them for transformation, not just 2D. Imagine that you can do it in 3D. You can rotate Princess Leia on Star Wars, basically using those transformation matrices. All right, that's why they are useful. So now, if we say that two matrices are equal to each other, if I say A equal to B, that means that not just they are the same size, 2 by 2 and 2 by 2 or 3 by 3, but also every element match. This must be 4, and this guy must be 0, and this guy must be 3, and right? So the only way for them to be equal if every element, 1 to 1 is exactly the same. So this is not the same, and this is not the same. If you say it's the same row, they are just flipped. That's not the same matrix. All right? It has to be exact copy of it. All right. So now let's learn some manipulation of those matrices, how we add them. If we add A plus B, if you add them, then that means that every element is added to the equivalence of this guy on the other side. So minus 4 plus 5, that's the 1. The 6 plus the minus 1, that's the 5. Okay. So obviously you cannot really add two matrices that have different what? Sizes, right? If they have different sizes, you cannot add them. They have to be 2 by 3 and 2 by 3, 4 by 1 and 4 by 1, 7 by 2 and 7 by 2, so that you can find something to add to. Now, scalar multiplication. We can multiply a matrix by a number, a scalar. Okay, so matrix is not a scalar. The matrix is rows and columns, right? But you can multiply a scalar. So by multiplying 5 times this, you mean basically that you multiply 5 times every one of those elements. right? So the 5 times the 1, the 5 times the 2, the 5 times the 3, the 5 times the 4. So obviously then it doesn't really matter whether we multiply the 5 from the right or from the left. I mean the matrix times the 5 or the 5 times the matrix will produce exactly the same number, right? And here is basically telling you minus a, that's as if you're multiplying minus 1 times a. You get this. A fraction, that's still a number. If you multiply a 0 times a, that means you multiply that scalar 0 times every 1. So it basically makes the whole thing 0. Okay? Very good. So based on this simple two operation, multiplication by scalar and addition, they are basically, this all applies. Alright? A plus b is the same as b plus a. Doesn't matter which is to the right and which one is to the left. This wouldn't be the case when we multiply two matrices. It's a big deal for multiplication of matrices. You cannot say that a times b is the same as b times a. Alright? Sometimes they cannot even do it from one side. Right? And you can add the first two first and then add the third, or add the second and third and then add the first. If you add 0, you will get the same thing. If you add the minus 1, you'll get 0. Of course, right? And this is for the scalar multiplication. This is all straightforward. Because it's just a number that you multiply by the matrices, then it doesn't really matter whether you add them and then you multiply by that scalar, or you multiply with the scalar times each one of them and then you add. Okay? And if you have two scalar multiplied, it doesn't matter which one gets multiplied first, of course. And multiplying by 1, you just get the same thing. Question so far? Alright. Here is the matrix multiplication. Okay, I don't know about you, but when I was undergrad, that was very confusing for me. It was like, I always was really worried that I would mix the rows by the columns. But here's how it works. So to start with, they don't have to be the same size. Okay? But what they need to do, because the fact that this element will come from the element in the second row will come from the second row in the first one. And he is in the first column, he will come from the first column of the second one. So basically the row of the element come from the row of the first, and the column come from the column of the second. Alright? We'll see an example about this in a second. But because of this, then we need the number of column here to be exactly the same number of rows over there. So 4 times 3 times 3 times 2, you can do this. Or 7 times 3 multiplied by 3 times 1, that also work. As long as this and this match. The column here and the rows there need to be matched. And what you will get will be the other two numbers. Okay? So those need to be exactly the same, and the product would be the 4 times 2. And if you don't believe me, just, go with it. And for example, you would say, well, this guy, this row, will generate which row in the final result? The fourth row, right? And how he will generate those two guys? Well, he will get this by the first column, and he will get this guy by the second column. Alright? So this is actually how you make a computer program to make this multiplication. It just basically, it's a loop that you go over all the rows and column of the product. The product is C. So C, J, and K is coming from basically the summation over AJL multiplied by BLK. Right? Where is the J is coming from? That's the row of the first column. Oh, sorry, the rows of the first matrix. And K, that's basically the column of the second matrix. Right? And so that's how it works. We will do a lot of this. You will get used to it. Question so far? So the matrices need to have exactly the inner dimension, kind of. And then those two guys next to each other. Same column, same rows here. And the product will end up having the same rows as the first one and the same column as the second one. Alright? So, for example, look at this. Here is he multiplying a times b. This is 3 times 3, 3 by 3 multiplied by 3 by 4. Can we do this? Yes, because that's 3 match, that's 3. Right? And what we will end up getting? We will end up getting a 3 times 4. A 3 times 4. And so, for example, this first row will generate the first row over here. Okay? So he will if you multiply this by the last column, that will generate this guy. Because the column came from this and the row. So how did we get this 42 again? 3 times 1 plus 5 times 8 plus minus 1 times 1. You will get the 48. Right? If I multiply the second row, this will generate my second row over here. Multiply the second row by the first column, I'll get this. Second column, I'll get this. Third column, I will get this. That's what the book is highlighting. So this times this, 4 times 3 plus 0 times 7 plus 2 times 1, you will get the 14. Because 3 times 4, that's 12, plus the 2 times 1, that's the other 2. So you'll get the 14. And finally, here, the third row here will generate all those guys in the last row, the third row, from multiplying it by this, 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 and this. Each one of those columns will generate. So for example, this time this first column will generate the minus 9. This guy in pink here multiplied by this will generate the 4. Minus 6 times minus 2 plus minus 3 times 0 plus 2 minus 4. Right? Why? Because that's 12 minus 8. You will get the 4. Okay? So if you have 3 times 4 multiplied by 3 times 3, can this work? No, because the 4 and 3 don't match. We will not find things to hit with each other, right? It doesn't work. But 1 times 3 times 3 times 1, yes, it works. And what we will get if we multiply 1 times 1 by 3 matrix times 3 by 1 matrix, we will get 1 by 1. Right? 1 by 1, that's one element. A matrix with one element. Where it come from? Well, the row come from, the first row come from the first row of the, it only has one row, so it's this. And the column, we have only one column, it comes from this column. So basically 3 times 1 plus 6 times 2 plus 1 times 4, that's the 19. 3 times 1 multiplied by 1 by 3, yes, it works. And you should get 3 by 3, that's this guy. And that's easy because it's simply, the first row will generate those 3 numbers. By this row times this column, you'll get 3. This row times 6. This 1. And then you go to the next element that will generate the 3 guys on the second row. Got it? Very good. Alright. So because of that rule, to start with, if you flip, let's flip this guy. I mean, let's call this matrix A and matrix B. So here's A times B. Can I do B times A? No. Because it will end up being 3 times by 2 multiplied by 4 times 3. It doesn't work. So not only it's not the same, not only it's not the same, A times B is not the same as B times A, but also one of them may not even exist. Okay? So we cannot flip them. And here he's giving you an example. Same matrices multiply A times B and B times A. You get completely different things. 0, 0, 0, 0 and 99, 99, 99 minus 99 minus 99. Right? So even if the multiplication exists because it's a square matrix, so it doesn't really matter whether you're multiplying from the right or the left, it's still 3 times 3 times 3 times 3. But the answer is completely different. Right? But things exist. For example, simple rule exists. For example, a scalar. The scalar, yes, you can multiply the scalar time the first one and then do the multiplication, or multiply the time the second and then the multiplication, or just do the multiplication and multiply the scalar at the end. So a scalar works. You can distribute the scalar on them. Alright? And you can actually do this as well. You can multiply the second and the third first before the first and the second. You are not changing the order, you're just basically changing which one gets multiplied first. This works as well. Alright? And you can distribute the multiplication on summation like this. Alright? Provided that it's possible to do that. Alright? Provided that they are the same size. Alright, so this is another example. Here is 2 by 2 multiplied by 2 times 3, and so this match, and therefore we will get 2 times 3. And basically just I'm trying to give you another example to make sure that you know the numbers. So just do this at home and make sure that you actually can get those numbers yourself. Right? So some people think this is easier, some people don't. But some people think that it's easier to do this multiplication if we actually think about this rule over here. So this rule basically say that when you multiply A times B, that matrix B is basically a bunch of vectors sitting next to each other. Alright? So you can actually distribute the A on them. You can basically say what we will end up having is AB1, AB2. So he's basically saying that, well, here's an example. Here is our A and here is our B. So that A is done, the A is multiplied by the first vector by itself, and then the same A, let me do this. So that A is here, it's here, and it's here. And every time he multiply the A by B1, by B2, and by B3, where this is B1, this is B2, and this is B3. Right? And what does he get when he do the multiplication? So it's easier on him to do it like this because it's just a vector time a matrix rather than matrix by matrix, and your eye can get lost. So a vector time matrix is a little bit easier. So this, which is now AB1, gets stacked over here. AB1, and next to it is AB2, and next to it is AB3. Right? This is AB3, and this is AB2. So whatever make you happy, do it in the exam. So either just do them by vector, or basically just follow that scheme where where the matrix, where the vector, which each element basically came from. His row came from the first matrix, and his column came from the second matrix. Okay? Very good. Still, when I was a student, I thought that why they are doing this? I mean, what are they torturing us? Why they have to multiply the matrices like this? I get the rule, but why? Well, here's why. It really makes sense to multiply it like this. So if I have a vector W and I want to convert it to X, the linear transformation between those two vectors, as if we are rotating or something, is basically to multiply the W by a matrix B. Right? So X is B times W, assuming you have this transformation between the two of them. And now if you would like to transform X to Y, another transformation, then Y is A times X. A, that it's a transformation matrix that will basically turn the X into Y. So now the question is, what if you want W directly to go to Y, rather than sending it first to X and then turning X into Y? Then there must be that Y should be A times B times W, or basically Y should be a matrix C times W. Well, the multiplication of matrices will satisfy this. C, when you say that C should be equal A times B, that makes sense because you are transforming it twice. This is a proof that this is a way to do the multiplication. So in order for C to be equal A times B, that's how you do the multiplication of matrices. So it's not like let's multiply every element by its element, which you think that's how it should be. Like we did the summation, when we added two matrices, we basically took every element and added to the next guy. But the multiplication is done differently because to satisfy basically linear transformation. That's one motivation for it. Questions? Alright. Now one nice thing also to learn is the transposition. So this is basically, we are rotating the matrix. And sometimes this would be, some books use it just to save space, especially textbook, they say the vector is, You know, x vector is basically 4, 2, and 1. Well, how he's going to write this in the textbook? That will require 3 lines, and the paper are expensive. You know, he cannot really afford to spend 3 lines to. So instead he will say xt. He can make superscript and subscript in textbook. That's not a big deal. He will say xt is, and then he will flip this guy. Right? He will make it basically horizontal. Right? So it's simply just rotating the column, the rows into columns. Right? So the first row become the first column, and the second row become the second column. Right? That's how we do this. All right. Very good. So again, he is turning the transpose of this. This is a row. So when we transpose it, we basically make it a column. The first row become the first and the last row. This matrix have only one row. So that row just become one column. And that column over here become one row. Right? So see that 6 become here and the 2 become here. So it's basically as if we are pivoting it from the middle and turning the rows into column and the column into rows. You have a question?
Would we be able to do that to combine matrices then? Like you said, if the inside numbers don't match, then we can't multiply or combine them. Could we do a transformation to combine the matrices?
So when you're transposing them, it's not the same matrix anymore. It's not like it's kept its property. No, that's another matrix. Right? Why would you do that operation? We'll see why it's useful in a second. Today you will see why it's useful. But it's once you transpose the matrix, it's not the same matrix. Okay? All right. So, yes.
On the left-hand side, it's turned counterclockwise. Some of the examples are turned clockwise.
So it's not really clockwise or counterclockwise. It's, for example, let's look at this one. So look at this. This row, what will end up be is the first row should be first column. So it seemed that it has turned what? Clockwise or counterclockwise? Clockwise. And the second row, what it should be? The second row should be, and look at this, he actually turned still clockwise, but then this guy
Still clockwise.
is still clockwise actually. So let me take this back again. Well, no, let's take this one.
Still clockwise.
Still clockwise part, yeah.
When you go backwards, it's counterclockwise.
That's a great idea. Maybe. Well, let me check. Actually, I think it's when the rows are more than the columns, that seemed to be clockwise. But when the columns are more, it seemed to be actually. So basically, Aij become Agi. That's the trick, right? So Aij become Agi. Do whatever it takes to do this. So what is that guy? That's A11. Well, he will stay A11. Okay, this guy is A31, so he should be A13. Hence the A13. Right? And of course, the lucky guy here, A22. Sorry, that's A21. He will end up being A12. First row, second column. Right? So let's highlight this rule over here. So that's how you make the transpose. Aij become Agi. All right. So based on this, if you make the transpose and then you do another transpose of the same of the transpose, you will get the same matrix. So you rotate it and then you rotate again. Aij become AGI, and then AGI become AIJ, right? So you will end up exactly with the same matrix. And you can add and then transpose, or you can transpose and then add. You will get the same results, right? Multiplying by scalar doesn't change anything, but look, the multiplication is always a problem. If you do the transpose of a product, it will be equal to actually the inverse of the multiplication times the transpose. And it has to do with the fact that 4 times 2 can be multiplied by 2 times 4, but you cannot basically change the order and expect them to work. Okay? Very good. So now there are few special form of matrices that will be useful for us. There is symmetric and skew symmetric matrices. So a symmetric matrix is basically across the diagonal. You can see that AI kj is the same as AJK. So basically A21 is the same as A12. A32 is the same as A23. So the diagonal element doesn't have to do anything, because I mean A11 is the same as A11. I mean, what A22 is the same as A22. It's always the case in any matrix. You know, A11 is the same as A11. We're talking about the same guy. But A21 is not necessarily the same as A12. And so not necessarily there is a mirror across the diagonal. But when this mirror exists, then it's called a symmetric matrix. Alright? Now, a smaller version of it, or like not really purely symmetric, it's called basically skew symmetric. And that is when basically AKJ is minus AJK. Meaning that when you look across the diagonal here, you see the element, same element was with a flip sign. 1 minus 1, minus 3 and 3, minus 2 and 2. Right? So a symmetric matrix, when you do the transpose for it, when you change AIJ to AGI, what will happen? Nothing. You will get exactly the same thing. Right? And a skew symmetric, when you do the transpose, what will happen is that it will be as if you will get a minus sign multiplied by the whole thing. It's as if you just put minus sign and you will get exactly the same matrix again. Right? Of course, for this to work, you know that A transpose is equal to minus A, that means that all the diagonal elements need to be 0. Right? Very good. So this is called symmetric, and this is skew symmetric matrix. More name to remember: a diagonal matrix. That's very useful in multiplication. It's really convenient to have a diagonal matrix like this. So a diagonal matrix basically have 0 everywhere except for the diagonal guys. Right? A scalar matrix, it's a diagonal matrix, but it was even the same number. So 5, 5, 5, 3, 3, 3. That's a scalar matrix. And finally, the unit matrix is a special case of the scalar matrix where basically the diagonal element is only 1, 1, 1. Okay? So this is the diagonal, this is a subversion of it, same number, and not just same number, it's actually 1. Then it becomes unit matrix I. Alright? A scalar matrix, when you multiply it, including the unity matrix, which is part of the scalar matrix, or a special case of it, when you multiply it from the right, you will get the same thing when multiplying it from the left. Right? And it's just basically that C multiplied by the matrix. You just basically put C everywhere. Okay? Alright. So this is not diagonal matrix, but almost look like diagonal matrix. It's basically have all those guys are not diagonal matrix. They are called triangular matrix because they have the diagonal and either the upper or the lower part filled with number, and the rest is zeros. Okay, in your homework today, you will try to turn one of the matrices into a diagonal, into a triangular matrix. We'll see how. Okay, but this is going to be very convenient for solving equations. If you are lucky enough to get a system like this, you will see how it's very easy to solve the equations because of it. Right? So what is a triangular matrix? It's basically the diagonal and everything in one side with number, and the other side is all zero. Okay? So there is something called tri-diagonal matrix, and the name is self-explanatory. It's basically a matrix with only three diagonal. The main diagonal, the guy on top, and the guy at the bottom, and everything else is zero. And if a matrix like this exists, the solution algorithm is called the tri-diagonal matrix algorithm. Okay, DTMA. This actually is very quick to run. It takes 5n, where n is so this matrix, if it's n by n, that TDMA can finish the solution in say 5n step compared to order of n square when you use traditional methods, right? So if you have a tri-diagonal matrix, the solution is very quick actually. And here is another form. It's called, well, it's not diagonal, it's not tri-diagonal, but it has tons of zeros. So when we do all those differential equations for heat transfer or fluid mechanics, you know, simulating the flow around a submarine, or doing the heat distribution in a piece of hot metal work that you are basically heating or cooling or something, the matrix that will get generated from the differential equation will become full with zeros. Only few number exists throughout the whole thing. So this is a sparse matrix. And if the matrix look like this, there are certain techniques that could make the solution much faster compared to a matrix that's full with numbers that need the whole mighty computer to solve it. But this one can actually go very quickly. So what I'm trying to say, that special geometry or special forms of matrices can actually dictate what is the best way to deal with them. Right? Rather than the general method, there are certain techniques that can solve special form of matrices very quickly. Alright, so now let's solve a system of equations. Right? So this equation will come from a pipe network something, and we are solving them, meaning that we want to find x1 and x2 and x3. That's the point. We have the coefficient matrix. All those numbers are given, and those need to be numbered. They cannot be another unknown. Meaning this a1 and a2 cannot be x1, for example, multiplied by x2, or it cannot be x1 squared. That's non-linear system. We'll leave this later. For this chapter, we are dealing only with linear system. So 5 multiplied by x1, 7.1 multiplied by x2, pi multiplied by x3, but they are all numbers. Alright? Now this guy, the b vector, all those numbers to the right, it's like 4, 3, 2, 1, there are a bunch of numbers. Well, that system is called non-homogeneous. If it's all zeros, if all the right hand side is all zeros, that's called a homogeneous system. Alright? So remember this, we'll use this in a second. So if there is even a single number here, that's become non-homogeneous. Alright? It's just an important name to remember. So what's our job? The job is to solve this equation, those equations. The job is to get x1 and x2 and all the way to xn. Right? All the way to xn. And you know, if we stick b next to the a, we get this a wiggly thing. That's the augmented matrix. Right? So look to this matrix and imagine as if you are actually still looking at this rows of equations standing next to each other. Right? So this a11 is multiplied by x1, and this a1n multiplied by xn, and it's equal to b1. And the same thing here, x1 is also multiplied by this guy, and this is multiplied by xn, and same xn that's multiplied here. And then this is the result, right? So the system doesn't always have a solution. Sometimes you don't have a solution, and sometimes you have a lot of solution, all right? And sometimes you have one unique solution, all right? So depending on what. For geometry, you can tell that if we consider 2 by 2, that's basically aligned, right? In 2D space, x1, x2, you can draw it by a line. The equation is just a line. In 3 by 3, that's a surface, right? If you have x1, x2, and x3, geometrically we can, of course, once you go like more than 3 by 3, you cannot really imagine the space, right? And you think it's really, that's imaginary, people don't do this until you go to a conference and you say someone complaining that, his 11 by 11 space is very hard to deal with. Like what? 11 by 11, solve 11 by 11 equation? Not 11 equation, it's solving the equation in 11 dimensions. He had 11 dimensions to solve the equation in. Right? So in 2D, in two-dimensional, it doesn't always come as two equations. Someone can hand you 3 equations in x1 and x2 in 2 dimensions, and they give you 3 equations. That's overdetermined system. That's more equation than the unknown, but it works. Sometimes it works. Sometimes people give you 1 equation in 2D. So in x1 and x2, he will basically give you 1 equation. He'll tell you, solve for me x1 plus x2 equal 5. That's it, 1 equation. So the number of equations doesn't always match the number of unknown. Right? So when this is the case, when they don't match, things can actually go either way. We'll see how that work. So to start with, so here is the system, and you can see here those 2 equations, x1 plus x2 equal 1 and 2x1 minus x2 equals 0. You can actually see the solution. This is a unique solution. In this case, x1 plus x2 equal 1 and 2x1 plus 2x2 equal 2. Those 2 lines, when you plot them, they will lie on top of each other. They match everywhere. That's infinite number of solutions. Any point on this will work. How did this happen? Why the system generated infinite number of solutions? Because it's not really 2 equations. That was 1 equation and another copy of it, another cheap copy of it, right? They just multiply by a 2 and they told us here there's another equation. Sometimes it's not clear to your eye that the third or the fourth equation is just a copy. It's not as simple as let's multiply by 2. Sometimes it's the first equation multiplied by 7 plus the second equation multiplied by 4 generate the third equation. So the third equation is still a version of the first 2, but not really a cheap version. They spend some time cooking it. But the number of true equation, this is called the number of independent equation. That really the beef, the actual equation that generated the system, and the rest is basically kind of a copy of it. All right. So that what will end up sending you into that route. Okay, that you have now infinite number of solutions, and sometimes 2 equation, 2 unknown. You think it's perfect. I should have a solution, but no, they don't work. It's not. If it's same equation, it will fall on the same place. But x1 plus x2 equal 1, that's this guy, and x1 plus x2 equals 0, that's this guy. They never meet. Right? Or in 3D, there will be like 2 surfaces parallel to each other. It's not the same equation. They just don't meet. I want my profit to be $1 million, and I don't want to have any workers in my factory. How are you going to give you $1 million profit if you don't have any? Doesn't really work. You have to employ people to get. So sometimes the equation don't have a solution. in 3D, that's how the geometry look like. So look at this. This is the unique solution. This is when all the three surfaces meet at one point. This when they meet at along a line. Okay, so that line, everything here is a solution. Everything here is a solution. Or if they are all collapse to one surface, well, everything here is a solution in 3D. Alright? And here they basically don't, there is no solution. Maybe two of them, look at this. Two of them have a solution here, but the other two have a solution here. But then the three of them don't have one solution. Right, very good. So let's try to drive those solutions, and then we'll see what situation where we will end up basically generating either no solution or infinite number of solutions. So this is called Gauss elimination. And when the system is small, 2 by 2 or 3 by 3, you can do it by hand, right? And so in the exam, expect that you will expect a problem where you would actually do Gauss elimination on it by hand. So you have to practice to do it also quickly, because the problem with those things that it takes a lot of time. So unless you practice a lot, you'll never re-finish the exam. So now imagine that the two equations that we were given to us, this 2 by 2, magically it was like this. What is that form? You remember the name? Yeah, upper triangular matrix. Everything else below the diagonal, actually there is only one element, but still. So the diagonal and one guy on top, and at the bottom is 0. So why this is very useful to come up with a solution, because if the matrix is in that form, upper triangular or lower triangular matrix, read the last equation for me. 13x2 equal minus 26. You got x2. x2 is minus 26 over 13. And then you go back to the first one, knowing that you already have x2 already in your hand, and you go here and x1 is 2 minus, I'm sending this over here. So I'm saying it's 2 minus 5x2 divided by the 2. Not just 2 by 2. Imagine if you have 20 by 20. But all of them, the whole thing is upper triangular or lower triangular. You can actually solve them like this, right? You start from the last one, the one with one element, and you get it, and then you go to the next one and the next one. And actually, the computer code for solving this is very short. So you basically can optimize it, that basically go get the last one and then go the first one, the one before it, and just add one more element. The one before it, just add one more element. So he finished very quickly, right? So this Gauss elimination is basically the point is to turn the matrix into a form where this back substitution, this is called back substitution, where this back substitution can work for us. So the Gauss elimination is simply to turn the matrix into an upper or lower triangular matrix, one of them. Once it's in that form, you just do the back substitution and you get the solution. So the question is, well, here's example 2. How will you turn this into an upper triangular matrix? I want to get rid of basically anything lower than the diagonal. Here's our diagonal, right? So anything lower than this diagonal need to get to 0. Fortunately for us, this is 2 by 2, then there is only one guy lower. We just have to get rid of it. If this was 3 by 3, we will end up with 3 guys that we have to turn them into a 0. But the technique is the same. It's basically, first of all, you basically put the b, you add the b vector next to because how are we gonna do this? How we can get rid of this guy? We multiply the first row by something and then we add to the second row. Can we do this? Yes, because the first row, if you keep the b with you, the first row is the equation. The right should be equal to the left. So the fact that we are adding the multiplying the left hand side by 5 and multiplying also the right hand side by 5, it's the same number then. And we adding it to our second row, that works because we are adding 7 and 7, for example. Alright, so that's why it works. So the second step, or the first step, is basically to put this P and put this line here, and then tell yourself, I want to get rid of this minus 4. So you stand on this diagonal element, this is called the pivot, and you basically use it to get rid of anything underneath. Alright, so what's underneath? It's the minus 4. How can I use this 2 to kill this minus 4? If only I had 4 in my hand, I could do the kill, right? So how can I get this into a 4? Basically you would say, well, 4 over 2, then it's 2. Then it's obviously you multiply the whole thing by 2 and you add it to the second row. So yes, you can do this because if you take the whole row and multiply, it's the same thing. So 2 times 2, that's 4. 5 times 2, that's 10. 2 times 2, that's 4, and then you add. Right? So when you do this, the 4 minus 4, 0. 10 plus 3, that's 13. 4 minus 30, that's minus 26. And you did it. Now you have an upper triangular matrix. Right? And you can start the next step, which is the back substitution. You start from the last row. That's what we did. So I gave you the solution before we started this one. So once you have here now, then it's easy. It's what we did over here. You got it? Alright. So it will get a little bit I mean, let's do this one first. See if it's like a little bit bigger matrix, then you don't do it only for one element but for all of them. So basically we start by this is the argument matrix. What's our job? We want to turn this into an upper triangular matrix. We need to use this pivot to get everything under it to be 0. Right? Fortunately we have 1, 0. Good, we are done with this row. But then we have to get rid of this guy and this guy. Minus 1, how can I get rid of that? Just add, right? We don't have to do anything. Just, we are lucky. If we just add this to this will kill this guy. And for this 20, what do I need? I need to multiply the first row by minus 20 and then add. And don't think, well, I will gonna multiply by 20 and then subtract. No. Let's multiply by the number that we add. Adding, you will not go wrong with adding. Subtracting, you will forget that you are subtracting. And you will add at a point. So let's multiply by the minus 20 and then just add the numbers. Right? So this will be minus 20 plus 20 will get you 0 here. Minus 20 times minus 1, that become 20. Plus 10, you will get 30. Minus 20 times 1, that's minus 20. Plus 0, that's minus 20. Don't feel sorry for losing that 0. That's okay. The point is that you want to use this to get zeros over here. However, you know, sometime before you start this blind, scheme, let's get everything under 0. It pays some time to have a look and tell yourself, I can change the rows. You can change the rows, right? It doesn't matter which row comes first. So you can take the fourth row and put it as the third, or the third instead of the. Why? Because it look more like a upper triangular matrix. So if it helps you to change the row before you start the multiplication, do it. Alright? And then, so look at him. He managed to get the zeros. Okay? He managed to get a 0 here and a 0 there. And the price was, he lost that 0. Right? And he got those numbers. So now he is basically looking at this and he's telling himself, well, I want an upper triangular matrix. That doesn't help me. I need a number here. I need a number here because I want to use that pivot. That's going to be my next pivot. And 0 underneath. So if I have 0 already on the diagonal, if I multiply that 0 by anything, I will still get 0. I will never be able to get rid of the guys underneath. So that's why he decided, well, let's push this back down there. Right? So he pushed this down there. He can do that. He can take the whole row, including the B, and put it down. And now back to the elimination, Gauss elimination, and you say, well, I got this 10, I wanna get rid of the number underneath, so I need to multiply by -3 and add. Exactly. At any point you can take the whole row, and I stress the B, don't forget the B. Okay, because sometimes people just change the rows here and forget this 90 that need also to go down with it.
And you can only do that if you have the B attached, because otherwise you're not doing the whole equation.
And you will always get the B with you if you are doing Gauss elimination. You have to put the B next to you, right? There's no point in playing with the coefficient matrix without the actual vector. All right, so he will do this, and we'll get this rid of 30, and he's done. He get it in upper triangular matrix, not just upper triangular matrix. This actually end up with one line that basically has 0 equals 0. Let's go back and see where did this come from to understand what's going on. So in that example, he basically said, here is an electric circuit and find the currents. The unknown is I1, I2, I3. Alright? I1, I2, and I3. So if you remember the Kirchhoff laws, at every node the current need to be equal to 0. Right? There's no storage. The charge coming in will need to leave. So I1 plus I1 minus or plus I1 plus I3 minus I2 equal to 0. That's point, I guess, P. And then at point Q, that's so I2 is coming and I3 and I1 are leaving. So minus I1 minus I3 plus I2 is 0. So those are the 2 points. And then the electric current, the voltage on this loop and on that loop, that's basically this 2 equation, the right loop. So I time R plus I time R equal to the 90, right? And the same thing over here, right? So why it's 25 and not 10? Because 10 and 15 and it's the same current, I3. So he said basically I3 time 10 plus I3 time 15. So that's why it's I3 time 25. The point is, he got 4 equations, 2 loops, 2 nodes, with only 3 unknown. So that system sounds to have more equation than unknown, right? That's called basically overdetermined system. Alright? So that overdetermined system sounds like trouble to me. So for example, you know, x1 equal 4 and x1 equal 5. 2 equations and 1 unknown. What's the solution? How could x1 equal 4 and x1 equal 5? No solution, right? Or for example, but sometimes it's not trouble. Like for example, look at this system. So 2 equations and 1 unknown. x1 equal 4 and 2x1 equal 8. Do we have a solution? Yeah, x1 equal 4. Well, how come we have 2 equations and 1 unknown? That sounds like you shouldn't have a solution. But again, this is a cheap copy of this equation. So our hope is that maybe here one equation is redundant, one equation is not linearly independent, it's actually dependent on the other 2 guys or 3 guys. You don't have to know before you start. Actually, if you do this Gauss elimination, things will solve themselves for you, as we will see in a second. Alright? So determined system, that's basically 2 equations, 2 unknown. It doesn't always have a solution. I mean, sound nice, but doesn't always. Remember, the 2 line may not really cross. x1 plus x2 equal 1 and x1 plus x2 equal 0. 2 equations, 2 unknown, but no solution. And when it's underdetermined, it's not enough equation. So 1 equation, 2 unknown. What do you think will happen here? What's the solution if x1 plus x2 equals 3? No solution, unique solution, or infinite number of solution? Infinite. I can think 1 and 2, or 0 and 3, or minus 1 and 4, or right? So So he's basically saying that system of equation will be consistent if it at least has one solution. Okay, whether it's unique or infinite number, and non-consistent if it has no solution. So basically he's saying, you know, like this is a non-consistent system. x1 plus x2 equal 1 and x1 plus x2 equal 0. It doesn't have a solution. Non-consistent. So anyway, so back again to our equation we are solving. 4 equation coming from this electric circuit. Alright? And it sound trouble. 4 equations, 3 unknown, it doesn't work. So what do we do with it? So you start as if it's okay. Okay, you just put the equation rows after rows after rows. Here are the 4 equations in the 3 unknown. I1, I2, I3. And from my experience with grading those problems, some of the students don't really know how to turn this into this. Okay, so that wouldn't take you far. I mean, you will not be able to do anything if you cannot turn the equation. So make sure that you can turn the equation into, I'm talking about the zeros, you know, where to put the zeros, and that's the hard part when x1 is not there, or when the equations are not really arranged right. So you have to arrange them, and if there is one element that's missing from that row, that equation, he gets 0 in his place. Alright? So anyway, so we just put the equation and we start this Gauss elimination, as we saw, you know, how he managed to get zeros. And when he had this line, he moved that line down because he was trying to go to the upper triangular form. But you know, line that's 0, 0, 0 equals 0. Why did this happen? Because one equation was linearly dependent on the other guy. So in the Gauss elimination, it will just disappear from you. Okay? If it was a true equation, a true constraint, so the system is really truly over-determined, x1 equal 4 and x1 equal 7, you will end up with not a row of zeros, but you will end up with 0, 0, 0 equal 12. Or 0, 0, 0 equals 7. Yeah? If it's like the equation is not really linearly independent. It's not really linearly dependent. No, it's an actual equation. It's really valid. It's another constraint. So you'll end up with 0 equal to 12. So you know that I cannot find anything, any x1, x2, and x3 that when I multiply them by zeros, because that's what this equation means. It say that 0 times x1 plus 0 times x2 plus 0 times x3 should be equal to, if it's 0 then fine, yes, any number can work. But if it's 12, sorry, I cannot find this magic number that I multiply by 0 and I get 12. So no solution. Alright? So anyway, it turned out that it's basically not really a true equation. It's linearly dependent, therefore 0 equals 0. What happens if you get 2 rows, not just one? I mean, the same system. Someone hand you the 4 equation in 3 unknown. You get 1 rows equal zeros. Fine, perfect. Right? We got rid of one of them. But then in the Gauss elimination, you also get another line of zeros. So now 2 rows of zeros. So now what is the case? This is actually then, it's 2 equations, 3 unknown. It's the same scenario when we said x1 plus x2 equal 5. Or x1 plus x2 equals, say, 3. 2 equations, 3 unknown. What's the case? Infinite number of solutions. Right? Very good. So anyway, so that line of 0 equals 0, he doesn't worry about it. Fine, we got rid of it. And now he has his upper triangular matrix. And what's next? What's next? Back substitution, starting from the last line. So basically say, well, minus 95 x3 equal minus 190, he's reading this, he get x3, which was the current I3, and then this one. So each one of those steps, and he basically get the numbers, right? So now if you come up with this answer for I1 and I3 and I2, 2 ampere, 4 and 2, and you want to check, you don't come and ask the TA or me what is the final answer. You take those current and what do? You substitute here. You check on them. And if they give you the 0 and 0 and the 90 and the 80, then it works. Right? Very good. Alright, so here is a case when you will get infinite solution. Again, that's x1 plus x2 equals 7. So how would that work? So to start with, someone hand you, look at this, 3 equations for unknown. That immediately give you the impression that we will end up with infinite number of solution. Alright? So again, you start the Gauss elimination. You basically say, well, I'm starting with that 3 and I'm gonna get zeros under. So what do I need to multiply with? I want to get minus 0.6. Alright? So that row should be multiplied by, so the way I would like you to remember so that you don't have to guess, it's basically you would say I wanna get minus 0.6 over 3. So it's the minus the guy divided by the diagonal. That's what I multiply with, which is minus 0.2, correct? But then, so you take this practicing and on the calculator you multiply by this, this, and this, and you add, and you do the same thing over here. You manage to get the 2 zeros, but look at the good surprise. Not only we had 3 equations for unknown, in the Gauss elimination we were just trying to get rid of this guy. Only trying to get rid of this guy, but it turned out the whole row zeroed from us. So now we have even 2 equations for unknown, not just 3 equations for unknown, 2 equations unknown. So let's read them. So those equations will look like this: 3 times x1 plus 2 times x2 plus 2 times x3 minus 5 times x4 equal the 8. And the same thing over here. And of course this is 0 equals 0. So what is the infinite number of solution? How we do this? You have to basically set, you have to tell him, yes, there is infinite number of solution, but what are those solutions? So you tell him, well, you have to specify T1 and T2. So you write this in the quiz or the homework or the exam. You'd say set or let x3, let's start with x4 actually, since it's the last one. Let's make x4 equal T1 and x3 equal T2, and then having this one T1 and T2, then from the second equation you can get x2, and from the first equation you can get x1 in terms of T1 and T2. So you basically give him the solution with 2 knobs, T1 and T2. Now he can basically put T1 and T2 any value he wants, 1 and 0, 0 and 1, minus 1 and 0, any vector that he wants, and he will get a solution in this 4 dimension. Okay? How do we know it's infinite number of solution? Because we got 2 equations, yes, and 4 unknown. So we don't have enough to come up with the number. We have to cook 2 of them to come up with the other 2. Very good. And here is the no solution case that I was telling you about. 3 times 3 equation system. Okay, that sounds promising. That sounds that maybe we'll get a unique solution. And starting with the 3, the pivot, he gets rid of the 2 and he gets rid of the 6. How? He multiplied the row by minus 2 over 3, and this guy he multiplied by minus 6 over 3. Okay, and in his process of eliminating those guys, he didn't even go to the second row. He was supposed to come up with this and zero it under it, but he didn't have to do this, because the moment he did this, the third row turned out to be 0, 0, 0 equal 12. Okay, so obviously no solution. Okay. So a determined system 3 times 3 doesn't always have to have a unique solution. Sometimes it doesn't have a solution. Right? Remember again the graphs. Sometimes the surfaces don't match, don't intersect. Very good. So the number of the linearly independent math equation, that is the reason why we run into this problem, whether we have no solution or infinite number of solutions. So they come up with this concept of basically the rank of the matrix. Alright? So to start with, he basically saying that if one of the equation is a copy, is a version of the other two, is a product, linear product of the linear combination of the other two, then it's a linear dependent. It's not independent, it's dependent. It's not a true equation. Alright? So, like for example, something like this, 3 equation and 3 unknown, but they are not really truly 3 equation. So, I'm saying we have been cheated. You know, someone handed us basically, it looked like 3 by 3, but it's actually no, it's only 2 equation and 3 unknown. So in this example, it's basically because of this. Because you can generate the third equation by saying it's 6. You multiply 6 times the first equation, and you divide the second equation minus over 2, and you will subtract, and you will get the third equation. So it's not really clear to your eye that this is the case. Huh? When it's x1 plus x2 equal 4, and then it's 2x1 plus 2x2 equal 8, it's pretty clear that this guy is a copy or a version or linearly dependent on the other one. But when you have something like this, you cannot tell with your eye. So how could you tell? Well, you do the Gauss elimination. Just go for the Gauss elimination and you will get something like this. So when you get 0, 0, 0, 0 equals 0, that then show that the system of 3 by 3 that we started with over here is actually only have 2 linearly independent equations. So we call this the rank. So the rank of that system is only 2. Only 2 equations are linearly independent. The third is not. Okay? So what is the rank of the matrix? Is the maximum number of linearly independent. Or basically what I'm saying here, it's how many real equation we have. Okay? Truly genuine equation, not copy. So that's the rank of the matrix. Alright? And so again, Gauss elimination will help us to reach that destination eventually. So sometime we'll get 0 equals 0, and time we'll get 0 is equal to 12. So in the book over here, if you go to the slide, he basically explained that. So after you go through Gauss elimination and you get basically a bunch of zeros like this, the difference between the total system to start with that we had and the number of unknown, so n is the number of unknown, okay, and m, that's the number of equation, and r, that's the number of, after Gauss elimination, how many rows that you get. The combination of those guys will basically set you in one of the scenario. Either no solution, when 0, 0, 0 equal to 12, or unique solution when you get 3 times 3, truly 3 by 3, or infinite number of solution when you end up with basically, one equation and 4 unknown. Alright, here is infinite number of solution. Yes.
If we, on this one slide where you had 0, 0, 0 equals 12,
yeah,
if we use that, would that be a rank 2, or?
So it doesn't really matter at this moment what's the rank, because this system have no solution. Alright? It's simply if you end up with m more than r, an element where you have a number where you don't have actually rows, then it's already no solution. Right? So for no solution, the rank is, or the number of independent solution is less than m, right? Where m is the number of basically unknowns over here. Sorry, the number of b factor that's non-zero. Okay, so if m is not 0, then the system has no solution. Simply 0, 0, 0 equal to a number at the end. Alright. So actually this section, that's where the homework is. So it's not really just Gauss elimination, it's a little bit step forward. It's called Gauss-Jordan elimination. So what's Gauss elimination? You turn the matrix into an upper triangular matrix. Will Gauss-Jordan go beyond that? Not just turning into an upper triangular matrix, but turn it into, what do you think? If you want to make the solution even diagonal, he turned it into a diagonal, not just diagonal, he basically, look at this. The job of this is actually to get the inverse. So Gauss, why the inverse is very useful to start with? Well, imagine that if you have A times X equal B, that's the system. We are trying to solve for X. If I multiply from the right, A minus 1, sorry, from the left, if I multiply A minus 1, A minus 1, A minus 1, over here I'll get A minus 1 multiplied by B. It's something, it's a number that will come, a vector that will come. And over here on the left hand side, A minus 1 multiplied by A, by definition of the inverse, I should get I, the unity matrix. 1, 1, 1, and everything is 0. And I times X, that's X. So basically X is A minus 1 times B. So if you have the inverse, you are that close to get the solution, because all you have to do is multiply the inverse by the B. Alright? So that's why if your system of equation have the same coefficient, but what's different is the B, the best way is to just come up with this A minus 1, and then for the rest of your life, all you have to do is just multiply that inverse by B, different B's, and you get the solution. Multiplication is pretty easy, right? So you don't have to solve the whole system over and over. All you have to do is put your hand in A minus 1. So think about a situation where the system is the same, the only thing that changes is the B, the force acting on the system, for example, the input to the system. Alright? So that's why we need the A minus 1. So Gauss-Jordan will give us the inverse. Okay, that's the job of this method. Will give us the inverse. How does it do the inverse? Well, you put the A, okay, and it's not the B, only the A. The B is not there, so only the A. And by the way, we cannot get the inverse of a matrix that's not square, so it has to be a square matrix, right? So it's n by n. So here is the A, and we'd like to get its inverse, so we put it like this, and next to it, that's a unity matrix. So if it's 3 by 3, it becomes 1, 1, and everything is 0. If it's 2 by 2, it's just 1, 1, and 0, 0. That's the homework. So it's 2 by 2, you will get the inverse for it. So you just basically have 1, 1, and zeros on the, right? Look like this. 1, 1, 0, 0. If it's 2 by 2. Right? 4 by 4, 1, 1, 1, 1, 1, and everything is 0. And then what do? You start doing Gauss elimination. Alright? You get rid of that 3 and get rid of this minus 1. You did it. And then you look at this 2 and you say, oh, I'm going to get rid of the stuff behind it, under it, and you do it. And then, and you did it over here. And then you look at those guys and you turn them into 1, 1, 1, and then you start using them to actually get rid of the guys on the top. So you turn the upper triangular matrix that you generated first, you turn the diagonal into 1, and then use them to turn this into even a diagonal matrix. And during all this process, on the right hand side, you were doing the same operation on those line, on the other side. You are just considering them part of the rows. The same way that we did it on the B, now we do it on the unity matrix. By the time you finish, and by finish you get I over here, this side is actually A minus 1. Okay? So again, why is that useful? Because now A minus 1, you multiply by B, you get the X. So the homework problem is, well, get the A minus 1 by Gauss-Jordan, and then use it to come up with a solution. Okay? Questions? Very good. Alright. There is another way to come up with the inverse. Okay? No, actually it's a little bit more complicated than this. The easier way is to ask MATLAB to come with the inverse, of course. Right? But you have to do it in the homework by hand. So here is another way to come up with the inverse. So the inverse of the matrix is to basically have A, J, K, which I will explain in a second, transpose, and then divide this by the determinant of the A. So to start with, what is the determinant? Let's remember what is the determinant. So if you want to get the determinant of the matrix, that's basically a number that tell you what's the value in here. So the determinant of the matrix, say this matrix A11, A12, A21, it's basically this guy multiplied by this minus this guy multiplied by this. Okay, so here is the formula. So if it's go up, so I'm just explaining how you come up with the determinant of the matrix first. Okay, so that was if it's 2 by 2, right? So simply if 2 by 2, it's A11, the diagonal one, minus the off diagonal. What if it's 3 by 3? So if it's 3 by 3, it's this guy multiplied by the determinant of that smaller matrix. What is the determinant of that smaller matrix? We did that before, right? It's the diagonal minus this. It's A22 times A33 minus A23 times A32. Right? So you can see how it's A11 multiplied by those two guys. Okay? And so that's only the first element in the first row. Minus the second element time minus the second element time his smaller determinant. His smaller determinant is basically what's left by crossing his row and column. It's this. So you can see that A12, what am I doing? He's opening it by A21. But if you actually you can still open it by A21 too. You can actually do it by any rows or any column. So if we pick this guy, it will basically be those. Right? So you can see it's A12, A13, and A32, A33. Alright? And finally, A31, his smaller matrix would be basically those guys. And that's what you see over here. Right? So you can determine the determinant of a matrix by using this column or using this row or this column or this row, any column or any three elements on them. But you have to follow that sign convention. So it's plus minus plus plus minus plus. Okay, so if I'm gonna use the second row, it should be minus plus minus. Is there any rule to this, or we're just doing it out of yes, there is a rule actually. The rule is whether it's plus or minus, it's minus 1 to power I and j. So I and j, that's the row and the column of your element that you are opening, you are determining the matrix with. So that's why if it's 3 by 3, you can see why it's plus, minus, plus, minus, plus, because, for example, this guy, that's the A11, right? So 1, 1, I and J is 1 and 1. You add the two of them and you get 2. So minus 1 to power 2, that's minus 1 times minus 1, you will get plus. And for this guy, A12, that's I is 1, J is 2, you get 3, minus 1, power 3, minus 1 times minus 1 times minus 1, you get minus 1. Right? Why this is useful? Because if you are doing it 4 by 4 or 5 by 5, then you have to, of course you will write a computer program to do this, but the point is, the rule is basically the sign will be determined by your I and J. So here is another example where he's trying to get the determined by the first row. He can do that, right? Why he's doing this? Because that 0 is very convenient. See? That 0, we don't even need to worry about. But the 1 is basically multiplied by this. The 6, 4, 0, 12. So it's 6 times 2 minus 4 times 0. 6 times 2 minus 4 times 0. 12. Right? And the minus 3, what does the minus 3 get multiplied with? The 2 minus 1, 4 and 2. 2 minus 1, 4 and 2. And why does 3 have a minus in front of it? Because I and J, it's plus, minus, plus, minus, plus, minus. Sorry, minus, plus, minus, and then plus, minus, plus. Okay? So anyway, for 3 by 3, maybe you should memorize it. You know, it's plus, minus, plus, minus, plus, minus, plus. For anything else, maybe you should just go and remember, oh, it's minus 1 I and J. Alright. So anyway, so you can see basically that, well, we don't even need to worry about this because it's the 0, but you can basically see how he can get the determinant. Alright, so, and here is another example, you can do this at home. So why this is nice to open with the first row? Why the first row is really easy? Because the 2 zeros, right? So it's only just one element. Okay? So now can you imagine if you have a diagonal matrix, 5, 4 and 3 and everything else is 0, what will be the determinant?
5 times 4 times 6.
Right? Because you will open with the first element and then the smaller one will have just one row like this. So it's basically, let's multiply the 3 of them. Alright. So we all this was basically just to determine this guy. So what is that? AJK to the power T. So let me just say that first. So if you have bigger matrices than this, you know, like 5 times 5 or 7 by 7, or you probably cannot do it by hand, it's just too long, and then that's the formula that the software would use, right? So the minus 1, J and K, right? And this is the row that you are opening with, and this is the minor of A, J and K. That's the thing that you are multiplying it by your elements, right? And you're basically doing the summation from all the way from k equal 1 to n. So this is the formula to come up with the determinant yourself with a computer program. All right. So the A, J, and K, that's the matrix of the cofactor of A, J, and K. So what is the cofactor? It's basically the minor multiplied by the sign. Okay. So what is the minor? That's basically the small matrix that remain after you cross the row and the column of that particular element. We'll see an example about this. So find the A minus 1 if this is A. Okay, so here is the matrix. So again, using this method, I need to find the determinant, and then I need to find the cofactors, and then I would say the inverse is the cofactor transpose divided by the determinant. That's the formula. So the first step is to come up with the determinant. Well, what is the determinant of this thing? So we remember plus minus plus, and we will open with, say, the first row. So minus 1 plus 2. Okay, minus 1 minus this 1 plus the 2, and this guy is multiplied by this smaller matrix. So minus 1 times 4 minus 1 times 3, minus 4 minus 3, and this is the minor, okay, of that element. So when we are doing the determinant, we are actually multiplying by its minor. So the minor is minus 7. Okay, this is the matrix that we will transpose and then divide by determinant to come up with the inverse. Okay, you got why this is minus 7? Because that matrix is the cofactor. The cofactor is basically the determinant multiplied by the sign of each element. Okay, the smaller determinant. So let's look at this guy. So again, I'm doing the determinant of this big A. So minus 1 multiplied by the smaller matrix, that will come up minus 1 multiplied by the smaller matrix, which is 3, 4, 1, minus 1. 3 times 4, that's 12. Minus 1 times minus 1, which is plus 1, that's 13. So I should put 13 over here, but don't forget that this element have a minus as a cofactor. So here is a minus 13. And finally, well, I'm not going to do the rest, but basically this 2 should be multiplied by what? The smaller matrix here, 3, 3, minus 1, minus 1. So 3 times 3, that's 9, minus 1 times minus 1, which is 9 minus 1. So that 8 should basically be here. Right? And so for each one of those guys, it's basically, again, if you want to get the minor for this guy, you basically cross his row and vector, his row and his row and column, and then you look at the smaller guy. Okay, what's in that smaller guy? Minus 1 times minus 1, that's 1. Minus 1 times 3, or minus 3, it's 1 minus 3, minus 2. And what's the sign here? Plus. Okay, let's, you want to do one more? We have 7 minutes, we can do all of them. So basically, for example, this 7, how did I get that 7? I come here and I cancel this guy and this guy. I have this minus this. Minus 1 times 1, that's minus 1. Okay. And then it's minus 6. Minus 1 minus 6, that's minus 7. Why it's plus 7? Because of that sign. Alright? So you get this matrix. Now let's flip it. Let's transpose it. Let's turn the row, first row into first column. Aij should be Aj and I. So A11 is A11, it's the same. A12 should be A21. A13 should be A31. Okay? A21 is now A12. This lucky guy stay where he is. This lucky guy also stay where he is, because A22 is A22 and A33 A33. But for example, you know, A23 is now, sorry, that's A32. It become A23. Right? So this guy come like this guy come like this. Alright, so this is the transpose of this matrix, the cofactor matrix. Alright, and then we divide over the determinant. It's this number, the 10, the determinant of the whole thing, and you got yourself your A minus 1. Okay, is that easier than Gauss-Jordan or more difficult? I mean, look at Gauss-Jordan. I mean, you have to turn it not just into upper diagonal matrix, but you turn it into diagonal matrix, and then I mean, it's also a lot of numbers too. But there's a lot of sign that you can
Right.
you can screw up. Definitely, yeah. All right. Anyway, so now once you had your eye on this a minus 1, you can use it for the solution, and also you can check that this a minus 1 is correct by multiplying it by a. So not surprisingly, when you multiply them by each other, they should get unity factor, unity matrix, right? We'll stop here.